everyone. So in today's talk, I will tell you some of our recent work on the structural chirality and its consequences in twisted van der Waals heterostructures. So maybe we can begin with this well-known figure that you guys probably seen thousands, millions times. So if you read this figure, the main emphasis is that because of the weak van der Waals interaction, right? So you can easily assemble materials with different properties together. And so in that sense, it's really talking about heterostructures, structures made of different materials. However, in addition to assemble different materials together, the beauty of van der Waals materials is that it actually introduces a new degree of freedom, which is actually the twisting angle, because you can see that if you keep using this Lego analogy, even when you try to assemble two Lego together, in this particular case, you still have a choice whether you want to do it in a 0 degree or 90 degree. And when we think about a real two-dimensional materials, then the twist angle can be arbitrary. So that's a really unique handle. And in fact, this whole field of twisted bilayer graphene can be just think as a spatial modulation of the local stacking order. It has led to tons of interesting phenomena, and some of them I'm sure you have already heard in this workshop. But while the focus has been on the formation of a flat band and the strong correlation, I would argue that there is actually a often overlooked property of this twisted bilayers, which is that they are actually the world's thinnest chiral structure. So in this talk, I will use 3 examples to demonstrate the consequences of structural chirality in van der Waals heterostructures. So I will first just give you a very simple example to show you why this is a chiral, and even at a geometric level, what is the consequence of the chiral structure. And then I will talk about chiral charge pumping and the so-called layered circular photogalvanic effect. And finally, I will also talk about chiral phonons in these Moiré heterostructures. So to just tell you a story, like the reason I drew myself into this study to really consider the consequence of the structural chirality is from a very simple observation. So you can see that this is a twisted bilayer with honeycomb structures, right? Now, if I start dragging the blue, let's say the top layer is blue. If I drag the blue layer to the left, you can see that this Moiré pattern is actually moving up. So it's perpendicular to the direction of the shift of velocity. And of course, now if the velocity reverse sign, you can see that it actually started going down. So this is actually very interesting sort of optical illusion. But as a physicist, let's understand what's behind that, and what's the reason for the phenomenon we just seen. So if you begin with physics way, we will see a phenomenon. The first step is, okay, let's write down the response equation and see how can I describe this thing mathematically. So let's say that the little v is the sliding in velocity, and the big V is the velocity of the Moiré pattern, right? So you can see that it's so big because the sliding velocity and the Moiré velocity is perpendicular to each other. You will say they are connected by a rank 2 tensor, and particularly it's the xy component of this rank 2 tensor. Okay, so now because this chi xy connect the velocity along the y direction, the little v, to the Moiré velocity in the x direction. So now if you perform for instance a mirror x reflection, so this guy will flip sign, but this guy will stay the same. So which tells you that in this case, if the symmetry has mirror x symmetry, then chi xy has to be 0. And similarly, you can argue that the mirror y has to be broken. So in fact, just geometrically, when you see this effect with your eyes, it already tells you that the structure has to break the mirror x and the mirror y symmetry. But that's not all of this, because what about the mirror z, right? You see that when you drag the top layer, equivalently, you can see when you drag the top layer to the right, equivalently, you can also drag the bottom layer to the left. And they should give you the same phenomenon. But this basically corresponding to a mu-z operation. Now, because under the mu-z operation, the dragging velocity, because especially the relative velocity between the top and the bottom layer. So if you do a mu-z reflection, the dragging velocity has to flip sign as well. So this is actually the actual way to write down the response. Now, a simple notation is that then we can introduce a layer index tau z. So tau z can be either 1 or -1, and it has a property under mirror reflection, you have to sign. Then you can see that what we have seen earlier in the animation, it's really given by is really dictated by a rank 3 tensor. Is the x, y, z component of a rank 3 tensor. Then for this tensor to be non-zero, then of course the mirror z reflection should also be broken. Okay. So you can see that it's a very simple sort of easy optical illusion you guys can play on your computer, but it tells us a very important fact is that when you consider twisted by the graphene, it's actually a chiral structure. So from here you can also see very clearly why all the three mirrors has to be broken. Now, let me remind you that to qualify as a structural chiral, it has to be regarded as a three-dimensional system. Because if you only break mirror x, mirror y, it will not qualify as chiral. But on the other hand, whenever you think about van der Waals structures, you always think, oh, it's a two-dimensional electron gas, which means that in the z direction, the motion is actually strictly quantized. So therefore, is there any consequence associated with this sort of this three-dimensional structural chirality in what we most regarded as a two-dimensional electron systems? So that's the question that we are trying to explore in this talk. Okay. So the first example I'm going to show you is actually quite simple. Is that I'm argue that if you have a moving Moiré potential, you can realize the topological Tholis pump. So this we've done this 2 years ago, and there are also papers from the Koshino group and the News group on the same topic. Okay, so let me first refresh your memory on what is a topological Tholis pump. Okay. So back in 1983, Tholis has argued that if you consider a one-dimensional insulator, and if the Hamiltonian undergo a cyclic variation, it can introduce adiabatic current, and the interval over the cycle period is quantized. So after one complete period, you're supposed to pump a unit number of electrons. So behind the Tholis argument, there is this beautiful theory of Berry phase and the numbers. But intuitively, the Tholis pump has a very simple understanding. So essentially, you can say you begin with a periodical potential. Let's consider the limit that the potential well is really deep. So you can really trap 1 electron per well. We're going to ignore the spin degree as well. Okay. So now you can start dragging this potential, right? Because the whole thing is periodic. So you can see that as you drag this potential, and after the potential moved by 1 lattice constant, the system would return to itself. So this would qualify as a cyclic variation of the Hamiltonian. But just by looking at the picture, you can imagine that if you drag it really slowly, and that's the adiabatic requirement, then you would just simply have moved the 1 electron from this to this after you shift the lattice by one lattice constant. So in this very simple case, the whole idea of Tholis pump almost become trivial. And in fact, if you knew the dragging potential, you knew the filling of your potential well, you can easily simply write down this is going to be the adiabatic current induced by this by this shift potential. Okay. So once we really understand this very intuitive picture of Tholis pump, then it shouldn't come as a surprise, right? If you start dragging 1 layer, Then you see the Mori potential is moving, and because each of the Mori potential can trap one electron inside, then that will actually give you a transverse current. So then what's left for us to figure out is actually what's the traveling speed of the Mori potential. So to figure that out, let me bring you back to exactly how do we understand this formation of the Mori potential. It's basically can be regarded as a spatial version of the beating of sound, right? So you can see that if I draw two period audio pattern with very similar period, and it's basically you can understand as the summation of two sine function. And of course, that you know this identity, and this k is going to be similar to k1 and k2. So there is a fast beating pattern, but in addition, you also gain a very slow pattern. So it's k1 minus k2, and that's the profile, right? And then it's very easy to see that in this case, the Mori potential should simply given or the Mori wave vector should be the twice of k, because because those fast oscillation go from negative to positive. So this tells you that if the two lattice if by epsilon, that should be the Mori potential. That's what happened in 1D. So what about the 2D? The 2D is the exact same. The only thing is that now you have to treat the wave vector and the position x both as vectors. So you do the exactly same thing. Of course, in 2D, that K1 and K2 can not only differ in length, they can also differ in direction. So this quickly tells you that if K1 equals, so in this case, the general formula for the Mori wave vector would be a multiplication by epsilon, but also a rotation by theta. Okay, so now what we need to do is simply, okay, we're gonna say we have two period potential, we have two signs, they give us the Mori potential. If I'm dragging one layer, I simply give a velocity term to one of those periodic potentials. So you do the same thing, and you can see that this will give you the so-called Mori speed up. So Vm equals k minus k over k minus k prime times d. And one of the interesting consequences is that actually when k and k prime are very close to each other, you should get a speed that's actually larger than the speed of light. And there's really nothing wrong with that, because we are not talking about the group velocity here. And here, now if we consider in 2D, so that's the general formula. So the little v again, and the little v here is the sliding velocity, and the Vm is the Mori velocity. It's given, so epsilon is the lattice mismatch, and then theta is the twisting angle. So once we figure out that what is this general expression for the Mori velocity, and then we assume that there should be a gap in the spectrum to realize the topological Fowler's pump. So that's basically coming from the adiabatic condition. And then we also need to know how many charges are there, right? But when you think about the graphene, we typically think about it in terms of this Dirac spectrum. So the energy is actually unbounded both from top and the bottom. And in this case, you can show that when we count the charge density, you should count from Dirac points. So it depends on how many field bands are counted from Dirac points. So then in twisted by the graphene, if you only feel the first band, then simply that should give you the final expression here. And so one of the things I want to point out is that you can see that the pump, the perpendicular current, is actually proportional to theta. So that's actually good news, right? Because when theta equals 0, then the whole effect should disappear. Okay, so now you can see that we actually, for the most general formula, we have both lattice mismatch and the twist angle in our expression here. And those two actually corresponding to two different cases. One is a twist by the graphene. So in that case, epsilon would be 0, but the theta would be not 0. So in that case, the pump current will be perpendicular to the sliding velocity. And another case is actually graphene on boron nitride. So without any rotation, because of the lattice mismatch, you already have a Maury potential. So in that case, theta is 0, but epsilon, the lattice mismatch is non-zero. So in that case, the pump current will be parallel to the shifting velocity. Another way to understand this, the difference between twisted violet graphene and the graphene on PN is actually looking at the symmetry. So you can see that if you just you consider twisted violet graphene, its symmetry group is given by D6, and the D6 actually allows a XYZ component. But on the other hand, for graphene on BN, if you just look at, say, this is graphene, and this outside is BN, so you can see that the symmetry group of this is actually C3V. And in that case, the relative tensor is actually XXZ, so it can only give you parallel current. Okay. So again, those are really just a very simple argument, but because we are talking about a topological effect, details doesn't matter. It's actually gave us a pretty robust result. But just to show you exactly how the things are working behind the scenes, we can actually begin with this McDonald model. So you have this kinetic part that's coming from the intralayer hopping, and there's a potential coming from interlayer hopping. And in fact, in McDonald paper, they already discussed that if you shift one layer relative to the other, then the Maury velocity will have to, the Maury potential would have to be changed by this expression here, where S is the shift vector. And in this case, it's really just corresponding to a gauge transformation of the original Hamiltonian. So therefore, when you are doing a shift, you actually don't change the energy spectrum at all. What you are changing is actually the phase hidden in these wave functions. Okay, so the other points we have mentioned earlier is that to qualify as a Flatus pump, you will have to have some global gap. So this is a calculation of the band structure at a different twisting angle. As you can see that there's actually some range of the twisting angle where you do have a global gap between the first layer, between the first miniband and the second miniband, so you have the cumulative energy into those gaps to have this Flatus pump. And also here I can show you that the actual chi response coefficients that can be written like a summation over the barrier curvature, and those are how the barrier curvature looks like in the Maury sum. And indeed, we find out that when you're including more and more bands, the chi XYZ will converge to this value, which roughly corresponding to 4 electrons per Maury supercell. Right? Because when you consider the field of first medium band, you have layer degeneracy, you have spin degeneracy. Okay, so this basically give us idea that how the Flatus pump looks like in the twisted violet graphene, and that's also. But then the question is, how can you really move those one layer relative to another layer? So Condensed group has been working on this kind of dynamical control in the past several years. You can see that they even made this kind of mirror. You can rotate the by layer. You can rotate one layer against the other one. So indeed, the Maury potential can be a time-dependent quantity. So exactly how large is this effect, right? So we can do some estimation. So first is that you want to have this adiabatic requirement, which is given by this inequality here. So which tells you that the sliding velocity must be smaller than 3 meters per second, and then this is actually way large above any sort of realistic movement of the layers. So we don't have to worry about the breakdown of the adiabatic condition. So once you put in this theta angle in there, you can see that for theta equals to 1.1 degree, our calculation is that the current density would be 10, and also for the sliding velocity 10 micrometers per second. Some of the high speed FM kits can reach that speed, and then for the width of 1 micrometer, you get 4 pico. So this is relatively a small current. So you probably want to have some sort of like the ability to detect the single electrons, like have a capacitor here rather than a current ammeter to actually measure this effect. So okay, so far we only in this discussion we only consider the pumping the single particle gap, but the pumping should also exist, right, when the ferromagnetic interaction gap or mobility gap. So that's something else that one should keep in mind. And we also only consider the adiabatic situation. But as you can see earlier, by the symmetry argument, the chi xyz should always be is always allowed by symmetry at least in this twisted structure. So it will be even interesting to see that whether the pumping effect can still exist when the system is metallic. So one of the things you can think is that if you roll this twisted by the graphene into another tube, and then if you rotate, say, the inner tube, so then that will generate a power in an anti-equivalent direction. So it should give you a power generator at the nanoscale. All right, so that's sort of that's the first example of the chiral effect in twisted roundabout structures. So in the second example, I'm going to move on to talk about the chiral optical effect in twisted bilateral graphene. So this was actually inspired by a really beautiful paper from Jiong Park's group several years ago when they did a following measurement. So they considered the twisted bilateral graphene, and what they did is they just shine the samples with left and right circularly polarized light, and they measured the absorption difference, which is a circular dichroism. So you can see that this curve is a monolayer graphene. It's almost zero, so that's what we expected. Monolayer graphene has inversion symmetry, but you can see that this is actually the CD signal for the left-handed, right, and the right-handed light, and you can see that there's some huge peaks developed, and this is for example of 16.5 degree. And if you look at the CD signal strength, it's actually about 2 milli degree. That's actually huge. In fact, if you compare this measured CDT in bilateral graphene, it's actually to achieve the similar signal, you have to have much thicker chiral molecule forms, like 50 nanometer or 100 micrometer. And why is this amazing? Because if you go back to the Landau Lifshitz, right? Because the circular dichroism in time reversal invariant systems can happen, but then the system must be chiral. So basically, what Landau argued is that this circular dichroism is also described by this phenomenon. It's like ICD, chi xyz, but it's proportional to partial EY over partial C. Again, we're talking about the bilayer system. So the difference between the electric field on the top layer and the second layer is responsible to drive the circular dichroism. Yet it can give you such a really significant signal. So that's really one of the amazing part of the twisted bilayers. Okay, so now this circular dichroism is still a linear order optical phenomenon. And we know that if you break all the inversion symmetry and all the mirror symmetries, nonlinear optical effect can also manifest. You can have shift current, you can have second harmonic generation, you can have a circular dichroism, sorry, you can have CPGE. And this is what we have focused on. Okay. So basically, you can imagine that because you break this chirality, if you're shining sample with a circular polarized light in a normal direction, then it can actually induce a dipole moment in the z direction. Of course, we know that in the bulk crystals, this is called CPGE. You should be able to get a non-fusion. You should get a perpendicular current in this way. But what's called a bilayer system would make more sense to talk about the formation of the accumulation of charges on the top and the bottom layer, which should give you a dipole moment. Okay. So you see that the existence of this effect can be easily appreciated just using Stimmich arguments. But to do the calculation, you have to it's a standard perturbative calculation. You basically calculate the response of the dipole moment to the electric field up to second order. And here is what we have found. We found that the coefficient actually can be written in this integral in the momentum space of this quantity here. This quantity actually has a very, very simple physical explanation. So omega is the frequency difference between the L bands, and the W here is also the strength of the left and right circularly polarized light. So you can see that because of the breaking of all the mirror symmetries, the W plus and W minus is actually has an asymmetrical profile in the momentum space. So you see here in this region, it will respond more strongly to the left-handed light, and then here it will respond more strongly to the right-handed light. And the P here is simply the change in the dipole moment during the transition, because actually here the conduction and the valence bands, when you go away from the momentum space, has unequal mixing between the left and between the top and the bottom layer wave functions. Now during optical transition, you are going to excite one electron from the bottom layer to the top layer, which then will create a non-zero dipole. Okay. So then exactly how large is this dipoles? So here I'm going to show you the calculation first for this 21.8 degree. And so for people working in the field, you know, this is a very special angle. It's sort of the largest non-trivial commensurate Morley structure you can find. So you can see that let's focus on the red line, focus on the black one. You can see that this is this CPG signal. It's zero, right? Almost zero until you reach like 3 eV. So then you have a really huge peak, and then you go back to zero until you reach like 4 eV. You can see a second peak develop. Yeah, I should have drawn more, so the second peak will quickly die down and then go to zero. So it has this really interesting resonant peak structure. So how do you understand that? It's actually pretty simple to understand this. So basically, you can see that this is what happens, right? When you have a twist by the graphene, you basically twist. You also have a twist in the momentum space. So the Chiral cone from the top layer and the bottom layer will be separated. Okay. So then let me actually draw this diagram here. So this is the one Chiral cone from the top layer. This second Chiral cone from the bottom layer. You can see that when the light frequency is actually smaller than this, so then the transition can only happen within the same layer, right? So it can only bring this electron to here, or you can bring this electron here. But because you can only have intra-layer transition, the electron wouldn't know it lives in a chiral environment. Remember, the chirality or the breaking of mirror symmetry, you have to have the 2 layers. But once you gradually increase your photon frequency until you can reach this part, so now you can see suddenly the charge carrier will realize that, oh, I'm actually in a chiral environment. I better behave in a chiral way. So that will give you a very large CPG signal. And of course, that if you consider the intersection between these 2 Chiral cones, you have one frequency. You can consider the intersection of this Chiral cone and this Chiral cone. It will have a second crossing point. So those are the 2 crossing points that we are talking about. Okay. And then to understand why there should be a resonance peak, it's also very important, because then you can see that if I change the twisting angle, then it should give me a very simple way to actually tune this resonance peak position. So then this is the calculation we show you that gives you the theta, the twisting angle dependence. Okay. So you can see that as you gradually decrease your twisting angle, the resonance peak will move from around 3 eV gradually down to even like 250 MeV. So we're really reaching the infrared range. And at the same time, because the whole signal is actually proportional to 1 over omega squared. So as you decrease, as you gradually shift your resonance peak to the infrared, towards the infrared frequency, the actual voltage difference between the top and bottom layer will actually keeps increasing. So this actually tells you that the LCBGE could be really useful for circular photon detector in the infrared range. Okay. And also one of the things is that you might wonder, because there maybe it could be spatial variation, because what we are doing is actually a sort of a spatially averaged calculation. So we actually went into inside each of the Moray cell, and here we are plotting the variation of the voltage difference as a spatial map. You can see that there indeed are some variations, but overall the sign still have the same sign. So the cancellation due to the twisting disorder is actually unlikely.
So can I ask you?
So yes.
If you go back to that plot of the red versus this one there, it seems that as you reach, I mean, you specifically plotted 2 to 22 degrees. So why first question is why you don't go lower angles?
Yes, yeah, thank you. I was going to talk about this because in a twisted biography, when you go below like a 2 degree, then the lattice relaxation effect kicks in. So what we have done in this calculation is a rigid twist, which is valid when you have a large twisting angle. But for small twisting angles, the lattice relaxation becomes very important. And while of course you can say, why don't you then just take into account of the lattice relaxation, and then because the LCBGE is a second order optical effect, the convergence becomes really bad. I know it's a practical issue, but definitely we should still have LCBGE below theta equal to 2 degree. But exactly what's the value, we don't know yet.
And it seems that as you go at the lower angles, your voltage starts to saturate. If you see the red plot at the 2, it doesn't go up anymore. Is that like a numerical issue, or it's a actual? There's a physics for it.
So far, I think as long as we go below 2, we are pretty confident about the calculation. But I think one of the reasons is that if you actually go into the expression of the response coefficient, right? The major contribution coming from 2 parts. One is the Berry curvature, one is the quantum metric tensor. So when you go to a small angle, then the band becomes flatter, and then the main contribution is going to come from the quantum metric tensor. But I guess when you go to really even smaller, the lattice doesn't change anymore. That would give you the saturation. But that would be my guess. We really haven't really looked at what really caused the saturation.
Thank you.
Can I ask another question?
Sure.
So slide before this, so you showed the resonance peaks.
Yeah, right.
So, yeah, I just want to make sure that I fully understood what you said. These resonance peaks are not related to the Van Hoff singularities you have in stands.
No, that was my guess when I first see this, but
yes.
when we actually get into the band structure, it's a crossing of the drug bonds.
Meaning 3V is crossing of the drug points?
Yeah, it's basically this is the resonance.
Okay, that crossing of the drug point. Yes, okay. But so these are not the Van Hoff singularities because this is a circular difference, so it's mainly related to the chirality of the system, right?
Yes.
Okay, so thank you.
Yeah, and also you can see, yeah. So we also calculate the joint dots. You can see that the joint dots develop very different.
Yeah.
Right?
Yeah.
So it doesn't have the deep structure.
Yeah, that's what is interesting. You don't see the circular dichroism where you see the density of state is high. Yeah. Thank you.
All right. Okay. Any more questions?
Hi, Professor. There was actually a question from the webinar audience. So I think it's asking about the Waals pump parts. The question
Yes.
is the transverse current oscillating?
Oh, well, if you oscillate this, the shift velocity, then the transverse current would start oscillating. But if you can drag this forever, it will always go. It's going to give you DC current. All right.
Thank you.
Thank you. I think we are good. We can continue. Thank you.
All right. So let me move on to the final example here. So the final example is chiral phonons. I mean, we are talking about electronic properties and optical properties, and we can look at phonon properties. So first the question is, let me just get this out of the way. What are chiral phonons? It's actually very simple. I mean, this is actually something you can do fairly easily. So you can consider the honeycomb lattice, right? You can consider like a boron nitride, for instance. So if you just solve this, like undergraduate solid state level, you can solve the phonon problem by introducing some ring constants, so they would interact with each other. The only requirement is that because we are talking about a boron nitride, so this black atom and the white atom would have different mass. Okay, you put them in, and that's the phonon spectrum you're going to get. Okay. So now, if you go to this mode at the k value, you see that this A and B is A and B here, but this is actually their normal mode. So the atoms are making circles in real space. Of course, so that's why it's called chiral phonons. And all the four modes have this circular motion. For instance, for this mode, for this optical, no, that's not for this optical branch, one of the atom will stay put, the other one will basically rotate around the equilibrium position. And the chiral phonons are actually very, very interesting for several reasons. First, if you just think about the transition metal dichotomies, when you have this inter-valley scattering, right? Because of the spin valley coupling, when you scatter across the valleys, not only momentum has to be conserved, but the angular momentum also have to be conserved. But during the scattering process, the spin would have to flip sign. So where does the angular momentum go? So you need a chiral phonon there to carry angular momentum to make the entire angular momentum conserved. And since we're talking about angular momentum, another very famous effect is actually the Einstein-de Haas effect. It's the only experiment Einstein has done in his life. But in Einstein-de Haas effect, you talk about the switching of the magnetization. Therefore, the spin angular momentum will have to transfer to the lattice. So in the Einstein-de Haas effect, we are talking about the total rigid rotation of the body. But you can also have phonons carry angular momentum to compensate the change of the spin angular momentum. So understand the chiral phonon is actually pretty important. But let's see that when can we have chiral phonons, right? So this is actually, again, it's actually pretty simple argument there. Is that if you consider an arbitrary pseudo vector mk, so this m can be angular momentum, it can be also Barry curvature. They are all examples of pseudo vectors. So the argument goes, if you have time reversal symmetry, so k would have to flip sign, and m will have to flip sign because we are talking about angular momentum. But if you have inverted symmetry, then k will flip sign, but M have to stay the same, because again, that's a property of a pseudo vector, right? So you can see that if my system has both time reversal and invariant symmetry, then MK has to vanish. But in boron nitride, it has time reversal symmetry, but it breaks inversion symmetry. So then that will allow a chiral phonon mode, and you can even see here that at K and K prime, the chirality flips. This one goes counterclockwise, this one goes clockwise. Okay. So therefore, we know that if you want to have chiral phonon, you must break invariant symmetry. And then you would say, wait a minute, we spent the entire talk talking about the chirality implicit bilayer systems. So I must have chiral phonons. Sure. So this is actually a figure from Koshino and Sun. So they actually calculated the phonon band in twisted bilayer graphene. You can see that the phonon band, right, can also develop a mini band. So those K bar, gamma bar is the high symmetry point. In the Moray program you can even see a flat phonon band that has been developed. However, if you focus on the K points, you see that these two acoustic modes will touch each other here. These two optical modes will touch each other there. But now if you compare this with the boron nitride case, obviously we have chiral phonons because of the breaking of invariant symmetry. Those branches should open a gap. But here, the gap is not open. So therefore, in twisted bilayer graphene, just by looking at the figure, you know that the phonons is not chiral. So what's the problem here? The problem is that earlier when we used the symmetry argument, we argued about time reversal and inversion, but because we're talking about the two-dimensional system, really we only have angular momentum, because those are due to orbital motions of the atoms, right? So the angular momentum is going to be in the z direction. So you can of course decompose inversion to a twofold rotation symmetry and a 0 z symmetry. And even if you break 0 z, but if you have C to Z, it would still forbid the angular momentum. So that's actually the reason why if you just consider twisted bilayer graphene, you wouldn't be able to see those chiral phonons. Okay. So let's actually do a more detailed analysis of exactly the symmetry of these Moray phonons. Because by definition, when we talk about Moray phonons, we are only interested in those low energy acoustic branch, right? Because you have a low energy acoustic branch, you add Moray potential, you're going to fold the phonon back to form those mini band. So in this case, we can write down our Lagrangian in the following way. So K is the kinetic energy, and the U intra is the intralayer elastic energy. In total, this K minus U intra will describe the intralayer phonon motion, and we're going to use the elastic theory. In that case, we're going to ignore basically the lattice structure. And then you can, if you just look at this, then obviously the system has a rotation symmetry around the z-axis. So those two cannot break C to Z, and therefore you cannot give you a chiral phonon. But we will consider interlayer binding energy. That's where things becomes interesting. So let me maybe talk about this just a little bit. So again, this shown here is a very large scale array, right? So again, and for the interlayer dynamics, we're going to use elastic theory. But for interlayer dynamics, when the phonon, so the atom in the top layer talk to the atom in the bottom layer, and a very simple and a very reasonable approximation is the so-called local stacking approximation. So you can see that, okay, in the AA stacking, so in this region, I should have a stacking energy. It's a number, right? But now if you move from A region to BA region, now the stacking change, you can imagine the stacking energy should also change, okay? But now if we choose the AA region as my origin, so you can look at the stacking energy at the AB. Now if you do a inversion or do a C to Z operation, so this point will come here, and this is the BA region. But we are talking about the graphene here, right? So in graphene, AB stacking and BA stacking, there's really no difference. So the stacking energy must be the same. So therefore, at the Maury length scale, for phonons, for acoustic phonons, the twisted bilayer graphene is actually has this emerged C2Z symmetry, or the in-plane inverting symmetry. But understand this is very important, because now you can think about what if I have boron nitride, for instance. The difference between graphene and the boron nitride is that in graphene, all the atoms are same. You have a 6 rotation symmetry. But in boron nitride, the A and B sublattices are different. And now if you think about a twisting in boron nitride, now you have two choices, right? So you can begin with the so-called A stacking. So boron on boron, nitrogen on nitrogen. You can twist it. Now if you twist it, you're going to have the AB and the BA region. And you can convince yourself that the AB and the BA region is actually related by mirror reflection. Okay? So therefore, those two should still have the same stacking energy. But if you begin with the so-called A prime configuration, that means the boron from the top layer sitting on the bottom of the nitrogen and vice versa. Now, if you do a twisting, you're going to have this BA prime and AB prime stacking here and there, and they are not related by any symmetry. So in that case, the stacking energy here and the stacking energy here will be different. So now I bring the C2Z symmetry, which will allow paraphonon to emerge, right? And so here is actually a DFT calculation from the Harvard proof, and so basically what you can see that this is for graphene. For graphene, AB and BA is the same, so you have a perfect symmetry. Now, if you consider moly disulfide, which have the same signature as a boron nitride, so therefore you really have to consider whether it's a 0 degree or 180 degree. Instead, for the 0 degree, which is basically A stacking we talked about earlier, again you can see that the stacking energy has an inversion symmetry AB equals BA. But now, if you go to the 180 configuration, then you can see that it actually breaks the inversion symmetry. So therefore, we can do a very simple classification of all the van der Waals bilayers. Twist the bilayer graphene has no paraphonons. Now, if you consider other homo bilayers, let's say BN and the TMDs, if you twist it from the 0 configuration, my stacking energy still have inversion symmetry. You don't have paraphonons. But if we consider twist the homo bilayer from 180 configuration or any hetero bilayers, you would have really inversion symmetry and have paraphonons. So let me show you our calculation for using the elastic theory I talked about earlier. So this is for MOS2, theta equals 2 degree. You can see that this is a 0 degree configuration, and there's no gap at the K point. Now, if you go to 180 degree configuration, the gap opens, indicating that I should have chiral modes. Okay, let me show you animation. It's my favorite part. So this is the this red arrow here is the displacement field in the elastic theory. You can see that this guy is doing rotation, right? And so this shows you that we have chiral phonon in the system. And also, if you actually pay attention to this, there's some interesting picture. You can see that this is the high energy stacking point. You see the largest amplitude. These two are the AB and the BA domains. It's pretty here, right? You don't see much amplitude. So this actually tells us like maybe, yeah. So this is the same figure. I just take t equals 0 and t equals a quarter of the period to show you where exactly are those amplitude. But at the end of the day, this is a schematics to repeat what I said. So the rotation mainly happens at those high stacking energy points. So this actually tells you that maybe we can develop a effective model, effective Hamiltonian, right, to capture this chiral effect. And it turns out that you can just think about where does all the potential energy come from. So then the potential energy could come from two places. The first is that you have AB, you have BA, therefore you have a domain wall. So the potential energy could be stored there. And the other way is that you have A, you have BA, and you have a domain wall. So the potential energy could come from two places. The first is that you have AB, you have BA, therefore you have a domain wall. So the potential energy could be stored there. And the other way is that you have A, you have BA, you have a domain wall. So the potential energy could be stored there. And in fact, you can easily work out the dynamical matrix for this domain energy, and this has been done by Koshino earlier. But in that case, it has a property dq equals d minus q. So it has invariant symmetry. And this shouldn't surprise you, right? Because if I ask you to make a triangular lattice of the ball and the spring model, you can't break invariant symmetry just by using those springs. But there's actually a different, there's another extra energy configuration, because you can see that when those imaginary balls are rotating, you're also changing the area of AB and BA stack. Okay, but for this TMD or BN, the AB and BA now have different energy. Therefore, you have to take into account those energy difference. And it turns out that in this case, the domain energy can be written in this formula here, and the VA. So this is the potential energy difference between the two domains. And the gamma Q, the actual form is not important, but it has this property. So gamma minus Q equals to minus gamma Q. We're actually bringing one symmetry. So now you can see that once then we can basically describe the low energy phonon mode just using the 2x2 matrix. And then shown here is actually the effective one. This dashed line. You can see that we only have one fitting parameter, which is the velocity here. It actually captured the physics beautifully, given that it's such a simple model. Okay? So this is actually a very, very important consequence, is that the 180-degree and 0-degree rotated TMD structure are actually very different. Their symmetry are completely different. So beyond the phonons, there should be other consequences as well. Okay, so then, yeah, this is just to show you that by changing the twisting angle, right, you can see that you can drastically modify the phonon structure. You can also change the orbital, change the angular momentum of those chiral phonons. Okay, so what's interesting about those chiral phonons is that because they carry this opposite angular momentum, and they also carry opposite barrier curvature. So if you can apply a temperature gradient, that actually give you a phonon angular momentum Ball effect. But more importantly to me, I think that the most interesting part is that of course in TMDs or in boron nitride, you already have a chiral phonon at the original K point of the Bruno result, right? But they are at the Zang edge, and they are very high in energy. But here, what I showed you is that even for the original acoustic branch, once you add this Mori potential, it can generate a chiral phonons, and it is at a much shorter wavelength and at a much lower energy. So which means that you can even think about like mechanical excitations of those chiral phonon mode. Well, previously in TMD, to excite those chiral phonon mode, you must have like you must use an optical method. So in that sense, you can really think about the twisted bilayer van der Waals heterostructures as a sort of a phononic crystal that can give you chiral phonons. So having said that, let me just give you a summary. So basically, hopefully I have convinced you that there are actually much more interesting things to think about in addition to the flat band. And this stacking degree is actually really unique to me now. So I showed you there are three consequences. So one is the chiral compounding, the CPG effect, and also the Mori chiral phonons. So thank you very much.
Thank you for a very interesting talk on three different effects of chiral. Let's take the person question first.
Yes, I have a question regarding the case that when you have a binary graphene without any twist, right? There is this layer of CP, what you call it, chiral photoelectric effect with no twist.
I'm sorry, could you repeat the question?
For binary graphing with no twist, is there any layers to PLG effect?
No, by the graphing, if you don't twist, it always have inversion center. It doesn't matter how you shift.
And even if you open up a small gap in it, because you can apply displacement if you open a small gap.
You can open a small gap. I think that the question is that to have the CPG, you really have to break all the three mirror symmetries. Yeah, you have to break all of them. So if you just apply, let's say, a gate, right, in a parallel graphing, open a gap, I don't think that you actually, one of the mirrors, one of like mirror X, mirror Y still has to be there.
Thank you for your talk. So with this presence of chiral phonons, would you be able to say anything special about BCS parent electron-phonon interaction? How that affects sensitivity?
That's something we're actively thinking, but I don't have more to say. But definitely, it should be able to affect the electron-phonon coupling. But I don't know the answer yet.
Thank you.
Very interesting talk. For the charge pump, can you actually make maybe a linear motor with it if you put maybe a hetero binary of TMP on top of each other and tune into the gap and drive a car?
I think the question is, can you make it? See, I already made one here.
Okay.
But yeah, but I mean, so you have all the numbers here, right? So I mean, to really estimate the number, you don't need any like to even know where it is. It's really just simple moving potential estimation. So I think it's mostly experimentally how fast you can rotate, how small the current you can measure, those kind of things.
For the phonon angular momentum Hall effect, so you need to have somehow the detector for chiral phonons, right? To see that you actually separated the two chiralities. So is there do you have ideas how to detect the chiralities of the phonons?
Yeah. So actually, one of the things is that. I think some really high resolution X-ray measurement might be able to just trace out the actual atomic movement, because that's really the beauty of the whole of this Moray phonons, right? So they are actually quite large in this space. It's a very expanded object.
Hi, Professor. So there are two questions from webinar. So one is asking about the words. Chirality can only be defined in 3D, but here, why does the chiral phonon seem to be defined in 2D increments?
Oh, I think the question is structural chirality. It's a three-dimensional concept, but I think that the word chiral has been used maybe that's too very widely for different contexts. The chiral phonon here just means that you have this rotation motion. We call it a chiral motion, but for structural chirality, it has to be a three-dimensional concept.
Okay, thank you. And there's another question asking, is the chiral phonon angular momentum quantized or not?
That's a pretty good question. Yes, the chiral phonon angular momentum. So there are two angular momentums. One is the pseudo angular momentum. That one has to be quantized because that one is actually purely due to symmetry. And when you're at the corner of the Morey-Brunel zone, you have threefold symmetry. So there the angular momentum is quantized modular 3h bar. But there's also a mechanical angular momentum, and for that, there's no quantization requirement.
Okay, I think we are done with this question. Let's thank D again.